Welcome back to the classroom. Today we're going to be looking at Module 7 of the Chemistry Syllabus, Inquiry Question number 6, Polymers, and the focus is on modeling, comparing the structure and properties and uses of condensation polymers. Specific examples we're looking at is nylon and polyesters. Now before we get into that, let's just quickly look at some things about structure. So there's a couple of important structural features we can talk about: crystallinity, branching, chain length, side groups, cross-linking, stability, and biodegradability. Now we kind of know what these all are from the previous lesson, but let me just go through them really quickly. So crystallinity is looking at how orderly packed are the chains. So these regions are said to be non-permeable, so you can't have water passing through. So the fact is basically there's no transfer of moisture, stuff like that. The molecular forces are very strong if it has really high crystallinity. It makes the substance more rigid. It will mean that there's a high melting point, and it also absorbs air and moisture and other chemicals really well, so it doesn't really allow it to move from one side to another. Branching, as we saw with the high density and low density polyethylene, just refers to how many additional chains are added to the main chain here. So if we have a high branch structure, something like low density polyethylene, there needs to be more extreme reactions that need to occur to cause these bonds to occur. But remember, because you have more branching, it also means the molecule is less dense, which also gives it a little bit more flexibility because there's weaker dispersion forces. Chain length. So the length of the chain is controlled by the conditions under which you go through polymerization. What we do know is the longer the polymer chain, the more viscous it is. Viscosity just means how well does it flow. So if it's a really long chain, we expect that the flow is a lot slower. If it's a shorter chain, it flows a lot faster, but also it means that it's a lot more difficult to mold it into something you want to use it for. So if we're trying to model or make shapes out of things, we won't use short chain polymers, we would use long chain polymers. If we want to use some kind of fuel source or anything, we would use short chain polymers as such. We have side chains, so that can be basically what we have as the backbone of the carbon. So we have this one here, polystyrene. It has the benzene ring that makes it more rigid because the benzene ring is a lot bigger. We have the low density polyethylene. You see it's only hydrogen. Hydrogen, obviously a single atom of hydrogen, is a lot smaller than the benzene ring. Hence, it's a lot more flexible in comparison than polystyrene. Another thing that can happen is cross-linking. So when you have two or more polymer chains linking into each other in 2 or 3 dimensional structures like we see here, this will increase the bond strength of the polymer and it makes it more rigid again. The last one we're going to look at is stability and biodegradability. Now, most polymers have a really strong carbon-carbon-carbon hydrogen covalent bond. That makes it quite stable. Now, the fact that this occurs means that a lot of synthetic polymers are not biodegradable because of how stable it is. It's not going to try and break itself apart very easily. So that's why we have an issue with synthetic plastics. They don't really break apart, and if it goes into marine waste, marine life will end up swallowing it and suffocating because of that reason. If we want to increase biodegradability of synthetic polymers, we actually put little strands of natural polymers in, like starch, and that actually allows the polymer to break down into slightly smaller segments, but obviously still to a degree not small enough. Another way we can make plastics is based on the way it's been generated. So there's 2 ways. There's thermosetting and there is thermoplastics. Okay, so apart from how they're made, they can be defined in these 2 ways. You have your polymer chain here, you have your cross links. Okay, so thermoplastics doesn't allow for cross-links, it allows for linear chain. Thermosetting, however, allows for cross-linking between the polymers. Okay, and that's done by the covalent bonds. The way it works is softened when heated as interelectrical forces are overcome, allowing the polymers to slip over one another. So that's the idea of when we do the heating process. Makes it easy to reshape and recycle. With thermosetting polymers, it decomposes or burns when heated when temperature is high enough to break the covalent cross-links, causing the polymer to decompose. This cannot be reshaped or recycled, but it is quite rigid and heat resistant, so you can see how different polymers can react to different styles of heat. Okay, now with that, let's look at the actual condensation polymers. As you can see, this isn't the right dot point, but it is what it is. We'll look at condensation polymers. We know that condensation polymers involves an addition reaction with two types of polymers that would give off a small molecule, most often water. Okay, so when the polymers join together. Polymer functional groups that are suitable for condensation polymerization, if it's an amide, hydroxide, carboxylic acid, COCl. So that would be some really nice ones that we have here. If we actually have a look at the formation of polyester, one of the polymers we're looking at here, we have our acid. So we have our two acids, all the same acid, and you can see we're getting rid of the hydroxyl group here and the hydrogen group here to form water. So we actually give off water from this, and then we get our condensation polymer chain here. You can see there's a little ester link, so that's the reason why it's called polyester, because of that formation of an ester group once the polymer has been formed. Okay, if we want to compare the difference between condensation and addition, it's quite simple. Addition polymers is when an unsaturated double or triple bond come together in terms of monomers. Condensation, it really depends on the functional group. Usually it's two different ones, but they must be able to release a small molecule in the form of water usually. And the backbone contains that set functional group, such as esters or amines. There is no byproduct in addition polymers, and its main backbone is basically the carbon-carbon chain. So you can see here with polyethylene, that's your main chain, that is the backbone of just carbon-carbon. You can see here with nylon 66, the backbone has the carbon functional group, or the carboxyl functional group there, or the ester functional group, has the amide functional group, so that's what we are dealing with here. Slightly difference between the two. Let's look at the formation of polyesters. Now this diagram here shows you one formation. If we're dealing with a dicarboxylic acid, so carboxylic acid that has two carboxylic functional groups, and a diode, so a molecule that has two hydroxyl functional groups, you can see on both ends. So the beauty of having something like this is it can form bonds on both sides. So if we have a look, okay, let's say this hydroxyl group breaks apart with this one here, okay, then that means this diode group can then break off and form with some other monomer of the same kind. So we get an ester dimer. Okay, that's what we have. That's our ester group right there. And that's the oxygen that is being displaced in that formation there. Okay, so what can we deal with? We can use, in terms of formation of polyesters, you can have a single monomer with the hydroxyl group forming with the carboxylic acid group on opposite ends to each other, so similar to what we have here. Or, well, not quite this, or is it? Yes. Okay, so with that there. Or you can have two different monomers with the diode and the carboxylic acid on both sides, like we showed in the previous slide. in terms of the structure, it's quite simple with the condensation polymers. An example of polyester is polyethylene terephthalate. And the thing is, if we look at the polymer ester group, so the ester group we have here, it's a polar bond. So between this carbon and oxygen and this carbon and this oxygen here, that increases the strength of the intermolecular forces of these polyesters. So it means that it has really high tensile strength. Okay, so you can make it into really thick fibers, really strong fibers. It has low gas and water permeability, so that means that gases and water doesn't really go through it as easily. We also know that it's an excellent electric and excellent heat insulator. And we also know it's really safe to use to contact food and beverages because it's pretty stable, it's not very reactive at all. So that's the structure of it, and that's kind of the reasoning. Let's look at some applications. So we have polyester bottles. Remember, they're really good at holding in food or beverages. That's why it's really good with that. It has a really high tensile strength, so that means that it can be really good, thick fiber fabrics that can then be made into clothing. So that's why a lot of clothing you have will have some bits and pieces of polyester. You're essentially using the same plastic as those found in bottles, in a way. The next one we will look at is nylon. So nylon, in terms of the group naming, it's very interesting. For the monomer chains, it's linear. The name of the nylon actually reflects the amount of carbon atoms on it. So if we have a look, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's why this nylon is called nylon 6,6, showing those carbon chains there. It's made up of adipic acid and a diamine, or amine. So it's the formation of these two that gives you the nylon there. There are multiple combinations of nylon, as we said, depending on how long the carbon chains are of the amine. So nylon, the reason why it's really good is it creates really strong intermolecular forces. The reason being is that nylon can, when it forms with its own polymer chain or monomer chain, the oxygen and the hydrogen with the nitrogen can form really good hydrogen bonds, really strong hydrogen bonds. Okay, so that really improves the tensile strength of the nylon and really makes it really resistant to high temperatures. So that makes it really good in construction work, fabrics of clothing. So that's what you have there. Okay, so what do we have? We have hydrogen bonding with this oxygen forming with the hydrogen if they need to. We have the dipole dipoles, so we have the dipole dipoles between the oxygen and the carbon. We also remember have the additional hydrogen bonding of the nitrogen to the hydrogen. We have dispersion forces. The longer the chain, the stronger the dispersion forces. It's semi-crystalline, so it's semi-ordered. So that gives it that structure where it's a little bit flexible, a little bit rigid here and there. So because of these specific intermolecular bonds that's in nylon, you have really high tensile strength, really strong fibers forming. It's really resistant to high temperatures, really good at absorbing moisture. Of course, you don't want your clothes to just leak out moisture, so that's really absorbs that moisture in. It's good resistance against chemicals, so it's good at storing particular chemicals you want stored away, but it can be attacked by strong acids, alcohols, and alkalines there. So for that, you might not want to use nylon to store those kind of chemicals there. In terms of usage and production, obviously footwear. With footwear, you want it to be strong tensile strength. You want it to absorb moisture really well. You have fishing nets, you have fishing lines, you have tents, you have threads for clothing. So there's a lot of applications for nylon that you can use based on these qualities that we talk about here. Okay, if we try and compare the pair, look at the difference between nylon and polyester. Nylon is commonly known as polyamides, Polyester is just made of polyester chains, so you can see the sort of slightly different. Now, nylon is a thermoplastic polymer. So as you would know, thermoplastic means that you can generate really long chains. Polyester is a thermoplastic or thermoset polymer, so it can form chains or it can just make really long singular chains. Nylon is monomers involved with the production of diamines and dicarboxylic acids, while as polyester is made from dicarboxylic acids and diodes. So the only difference between the two is nylon uses amines, polyester uses diodes. Okay, and it's essentially composed of nitrogen atoms, while there's no nitrogen atoms in existence for polyester. So that's sort of the difference between the two. Okay, so that's a quick summary of everything we need to know about addition polymers and also condensation polymers now in this topic here. Feel free to have a go at this little question. Contrast one additional polymer and one condensation polymer in terms of their structure, properties, and uses. Include a structural formula in your answer. So have a look back at the slides on any structures of nylon, any structures of polyesters, and compare that with one addition polymer. Right, that concludes our lesson. Thank you for joining the classroom. If you have any questions, feel free to comment below. If not, stay safe, study hard, and I'll see you in our next lesson.